So, good morning, respected faculty members and dear friends. Today, we are presenting our project titled Network Science with iGraph, a comprehensive tutorial. This project has been carried out by me and my teammate Dipanjan. We are from Indian Institute of Technology, Bhilai. This work was completed under the guidance of Professor Rishi Ranjan Singh, and network science is an important field for analyzing complex systems. In this presentation, we will focus on the iGraph library. We will explain its concepts, features, and applications. So, and what is our outline? So, this slide shows the outline of our presentation. First, we will introduce iGraph and its background. Next, we will discuss its importance in network science. Then, we will explain the key functionalities of iGraph. After that, we will see some real world applications. We will also discuss the advantages and limitations. And finally, we will summarize our presentation. Let us begin with the introduction. So, what is an iGraph? iGraph is a powerful open source library for network analysis. It was developed in 2003, and iGraph is designed to work with graphs and networks, and it is available in C, R, and Python programming languages. The core implementation is written in C for high performance. It supports both analysis and visualizations of networks. iGraph is widely used in academic research also. It is also used in industry applications as well. So, why should we choose iGraph? So, iGraph is chosen mainly because of its high performance. It can efficiently handle millions of nodes and edges. The library provides more than 400 inbuilt functions, and it is completely free and open source. iGraph has a strong and active user community, and it is well documented with examples. It works on Linux, MacOS, and Windows, and it integrates well with Python libraries like NumPy and Pandas. Now we'll move further. iGraph versus other tools. So here we will compare iGraph with networks and NetworkX and Cafi. So iGraph provides excellent speed and scalability. NetworkX is easy to use but slower for large networks. Cafi is mainly used for interactive visualizations. iGraph is mainly code based, not GUI based. So this makes it suitable for algorithmic analysis, and iGraph performs better for large datasets. So hence iGraph is preferred for research work. And why we study networks? So many real world systems can be represented as networks. So example include social, biological, and technological systems. Nodes represent entities and edges represent relationships. And network science helps us understand connectivity patterns. It allows us to analyze information flow. It helps us to study robustness and failures. So network explain how systems evolve over time. So thus networks analysis is very important. So key concepts that we have used in network science are a graph that consists of nodes and the edges between them. This is the basic representation of graph. And nodes are also called vertices. Edges represent connections between nodes. The degree of a node is the number of connections it has. A path is a sequence of connected edges. These are the basic terminologies we are discussing, and distance is the shortest path. Component is connected. A subgraph and centrality measures the importance that we will discuss later. And what are the real world network properties? So, a real network shows heterogeneous degree distribution. Some nodes act as hubs with many connections. Networks also show clustering behavior. So, this means neighbors tend to be connected. That we have also studied in machine learning. And most networks have short path lengths also. And this is known as the small world property. And networks often contains communities. These properties differ from random graphs. And the iGraph's role in network science. And iGraph enables large-scale network analysis. It provides efficient implementations of algorithms. It ensures standardized and reliable results. Researchers can easily reproduce experiments, and iGraph reduces coding effort significantly, and it also bridges theory with practical applications. Complex algorithms are available as simple functions, and thus iGraph accelerates research works. And what is the impact of iGraph on research? Like iGraph is widely used in academic research in cities. It is cited in thousands of research papers. It is used in biology, sociology, and physics also. iGraph is popular in neuroscience studies. It also used in epidemiology research also. Many universities include it in their curriculum also. It supports reproducible scientific analysis, hence iGraph had a strong research impact. So now we will study some types of networks. So networks can be directed or undirected. They can be weighted or unweighted. Some network allows multiple edges. Random networks are generated probabilistically, and scale-free networks follow power-law degree distribution. And small world networks have short paths, and different applications use different network types. And iGraph supports all these networks. And how do we represent network? So as we all know that networks can be stored as adjacency matrices. Matrices are useful for dense networks, and lists store neighbors of each node. They are efficient in sparse networks. So edge store source and target pairs. iGraph internally optimizes these representation. Choices depends on network size. It also depends on algorithms used. And now we'll talk about we have talked about the key functionalities, and now we'll talk about the structural analysis. So iGraph provides powerful structural analysis tools. Like it can compute connected components, shortest paths and distances are supported. It can calculate network diameter. Centrality measures are easily computed. Example includes degree and betweenness, like clustering coefficients can be measured, and these metrics describe the network structures. And now we will discuss some important formulas that is called centrality measures in network science. So for that I'll use one slide. So in network science, centrality measures are used to quantify the importance, influence, or structural role of nodes within a network. So different centrality measures capture different notions of importance, such as connectivity, closeness, control over information flow, or influence over the other nodes. So what is first we will discuss degree centrality. So it is defined as degree centrality is the simplest measure of node importance. It is based on the idea that a node with more direct connections is more important. And mathematically, the degree centrality of a node is defined as C equals to and as follows. So in direct networks, we distinguish between in-degree centrality and out-degree centrality, representing incoming and outgoing connections respectively. And what do we mean by closeness centrality? Formally, closeness centrality is defined as the inverse of the total shortest path distance from a node to the all other nodes, and it is written as 1 over summation and one more is betweenness centrality. It is defined like it measures how often a node lies on the shortest paths between other two nodes. Like nodes with too high betweenness centrality act as bridge or brokers controlling the flow of information in the network. And mathematically it is written by In numerator is the total number of shortest paths between nodes S and T, and in denominator we have the number of those paths that pass through node V. And one more, we will discuss what is eigenvector centrality. So eigenvector centrality extends the idea of degree centrality by considering not just the number of connections but also the importance of neighboring nodes, and it is represented by. This equation states that a node centrality is proportional to the sum of the centralities of its neighbors. Here, lambda is the largest eigenvalue of the adjacency matrix. And now, last we will discuss what is PageRank. So, PageRank is a variant of eigenvector centrality that models a random walk process on the network. It was originally developed by Google to rank web pages. A node has high PageRank if it is linked by other nodes that themselves have high PageRank, and mathematically it is represented by. And one more, we will discuss about CAD centrality. So CAD centrality considers all paths in the network but assigns less weight to longer paths. So it ensures that even nodes with low degrees receive some centrality value, and mathematically it is written as. Where alpha is an attenuation factor and beta is a constant representing baseline importance. So, in summary, different centrality measures capture different structural roles of nodes. Degree centrality measures connectivity, closeness measures accessibility, and betweenness measures control, and eigenvector based methods measures influence. So, the choice of centrality measures depends on the nature of the network and the research question. So, by this, we'll today end our session, and these are some applications that we can study, like iGraph is used in social network analysis, like its use cases are analyzing Twitter follower networks, like, and more applications you can read, like in terms of biological networks, and also in terms of transportation networks, and also in terms of epidemiology. So we discovered, and we will discuss now advantages and limitations of iGraph. So advantages are, it is highly optimized, it is written in C, it is memory efficient, it has fast algorithms, and you can see that most of the codes are run in limited time complexity, and most of the functions in here are inbuilt, and it also works seamlessly with Python, with and also with its libraries, and it is open source and free. And limitation, one of the limitation is visualization, like built-in visualization less sophisticated than GIFI or Cytoscape. And also and one more limitation is the learning curve, like it is suitable for a person who know programming before. And one more limitation is, like it is primarily designed for static networks, and it has some memory constraints as well. So by this we will end our session today, and installation part will be done in the second video. Thank you.
Hello everyone, myself Dipanjan Mondal. Today I am going to give you a brief idea about the installation process of iGraph in Ubuntu system, and a hands-on tutorial on iGraph, how we use it to make a graph and do analysis on it. Please note that these steps are specific to Ubuntu environment. To do this, to do this installation process, we need to update our Ubuntu system first. So open our Ubuntu system. So first we need to update our system. This will ask you for your password. So I have all my packages are up to date. So if we have any packages to update, for that we have to run sudo apt upgrade. This process will fix issues within your Ubuntu system. It also improves your security and keeps our system running smoothly. Next, we need to install some required packages that will help iGraph to compile our code correctly. So first, the preload packages are build essential, Python 3 dev, libxml2 dev, and zlibz dev. So for that, we need to run this command. So if we enter, this will install the all required packages. We already installed it. To check whether these packages are installed or not, you can run this command. So this will give you a list of packages that are already installed in your system and helps iGraph to compile correctly. After installing the required packages, we need to install iGraph. So here you can see requirement already satisfied. It means we already download it and iGraph is present in my system. Next, to verify our installation of iGraph, we have another method. We can run Python 3. This will uh, this will turn your terminal to a state where we can check iGraph's version that we installed recently. So first we have to import iGraph, then print iGraph dot underscore version. This will give you the version of iGraph that you recently installed. So exit from it. Let's go to the next part of this tutorial session. So we have some preloaded code that will help you to understand how graph is generated and what analysis we can do through iGraph's tool. So for that we have to go to our tutorial sessions folder. Yeah. So let's go to the Science folder, then going to go proceed in new folder, then step by step understanding. Here you have some code. First one is igraph version.py, second one is print a node.py, third is print to node with age.py, fourth is print three connected node, fifth is degree of each node, sixth is shortest path.py, and last one is centrality measures. So let's run one by one and see what we conclude to our tutorial. Okay, so first one is iGraph version. So in this code, we basically do is import our iGraph and we will print our version. So for that, I write code. Yeah, this will give you the required output. So our required output is iGraph version correctly. So we previously see that our iGraphs version is 1.0.0.0. So if we run this code, then we will get, if we get the same output, then we will say that this is correct, that our installation is goes well and we don't have any error. So let's run this. So here you can see you got a version of iGraph which is 1.0.0, which you can previously which you see previously. In our next step, we will see how a node is print. So for that, we have a code print a node.py. So in this code, we will import our iGraph as IG. So for this, we can use IG as a short form of iGraph. Next in this line G equals to IG graph, we basically create a graph, empty graph. We add a vertex G add vertex 1 and we print vertex index here and vertex index and vertex name. So if we run this, Oh, okay. So let me remove all the PNGs that have been stored previously. Okay. Okay. This will goes to and we will delete all our output PNGs to show you that our code run perfectly. Yeah. So you can see our folder has no PNG files. Now let's run our first code, which is Python 3. Yeah. And second one is Python 3. Here you can see we have one, we in our code we do add one vertex and we name that vertex as 0 and we print that vertex using the index value, and here you can see vertex 0 is printed. If you want to see the image that is generated by this code is this. Here you can see one node is getting printed here. Now in our next part we will just we'll see how two vertices are printed in a graph and two vertices that are printed are connected. So for that we need to run, we will see first code, right? Cat. So in this section we just import our iGraph library as IG. This is the short form of iGraph we can use later. Next we create a empty graph here. So G is equals to ig.graph. This will create a empty graph. Next we add two vertices by adding this line g.add vertices parenthesis 2, and between these two vertices we add a edge between 0 and 1. So 0 and 1 are the node and we add a edge between 0 and 1. The name of the node 0 and 1 are A and B. Here we can see we just set the names of the node and we print the vertices and edge, and this section is used to save that PNG, save that graph in PNG format. We label the vertex and vertex size and edge width. So if we run a code, it will give you. Yeah. So we have vertices A and B, edge between A and B we have edge 0, 1. So let's see the PNG file. can see PNG. This is the output. Here you can see A, B. So in this section, we just print the label also in the graph. So we get the label here and the edge between. Next we will see our three connected node. So for that, let's see how the code is written. As our previous codes, we will import our iGraph first and use it as IG. So we will create an empty graph, IG graph. We add vertices. We need three vertices. So G add vertices 3. We need to add between the vertices. So we add edges between 0 and 1. So 0 and 1 and 1 and 2. So 0, 1, 2, and between 0 and 1 and 1 and 2 there will be an edge. We label the nodes and give an attribute name. Then we print the vertices and we will print all the edges. If in graph there is a edge, then we'll print that edge also between the two vertices. So if we run this code for print three connected node, we'll get icon 3. We get this output. So we have vertices A, B, and C, and the edge between AB is 0, 1 and BC is 1, 2. So let's go and see the yes. Here you can see the nodes and the attribute name of each node. For 1, for 0, it's A. For 1, it's B. For 2, it's C. We first add these three nodes, then we label it as A, B, and C. Then we will add the edge between 0, A and B and C. And we get this output at the end of the process. Let's go to the next part of this section, which is degree of each node. Okay, so degree of each node means the we want degree of each node means the direct connection of a node that have. So degree of a node is how many direct connections a node has. go with the go through a code first. In this section, we import our iGraph as IG. We create our first and we create our empty graph here. We add four vertices and add edges between them. We name the vertices as A, B, C, and D. We print the node degrees. So this will print first, and for every vertices in G, we will print G dot degree V index. So G dot degree V index is used to get the degree of each indexed V. If we run Python 3, as you can see, as I say, node degree as print first here. So this print node degree printed this line. Next we have v name. So for first iteration we have a here, and if we see the image, degree of nodes, if we see the image, sorry, yes. So we have node degree a. So the degree of a node is 2. Here in our picture we have a direct connection of A between A with C and B. So you can you can say that the degree of A is 2 is correct. Now degree of B is 2. You can see B has a direct connection with A and C. So the degree of B is 2 is correct. The C. So if we have C node, so C has a direct connection with three different nodes. So we have our degree for C is 3. We have also D. D has a connection with one only C. So the degree of D is 1. So our output is correct. Let's run next command. Next code is for shortest path. So for this we have a code, this one. So first we import our iGraph as IG, then we create our empty graph, we add the vertices, then So we add 10 node here. We just add edges between them. So we have 0, 1, we have 0, we have edge between 0 and 1, 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6, 6 and 7, 7 and 8, 8 and 9. Between all these pairs, we have a edge. So next, if we see, next we will see the name of the nodes. We will name each node 1 to 10. So let's, and then we have the path here. Here you have the functions to get the shortest path. You write 0.0 and 9 is the which node, between which two node you want the shortest path, and these two numbers denoted that, and this 0 is from which node you want to start your shortest path journey. So if we see the PNG, let's run this code first. Python 3. Here you can see the shortest path from 0 to 9. If we see the PNG explorer.exe dot get, you can see a PNG here, shortest path between 0 to 9. So we have 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, and 8, 9. In every each pair we have a edge between the nodes. Now let's see if we have uh, mm, now let's go to the next phase of this tutorial session. Cat centrality is cat centrality measures. So in centrality measures we have different centrality measures. First one is degree centrality. Degree centrality means how many direct connections a node has. The simple meaning of degree centrality is how many friends someone has. And the formula of degree centrality is degree centrality of V is the number of connections of V divided by total possible connections. Next, we have our centrality measures as closeness centrality. This defines how close a node is to all other nodes. In simple meaning, how first someone can contact everyone. As an example, we can say if A reach other in few steps, then A has a high closeness. Formula of closeness centrality of V is total nodes minus 1 divided by the sum of distance from V to all other nodes. Next, we have betweenness centrality. So, how often a node lies on shortest path. This will give you idea of betweenness centrality. In simple meaning, who acts as a bridge between pupils or communities. If B connects two groups, then B has high betweenness. The formula of betweenness centrality is betweenness centrality of V is the sum of the fraction of shortest path between S and T that passes through V. Next, we have eigenvector centrality. Eigenvector centrality is importance based on important neighbor. Being famous because you have friend who was famous. If A connected to a popular nodes, then A has a high eigenvector centrality. Formula of eigenvector centrality is eigenvector centrality of V is the proportional to the sum of centrality of its neighboring nodes. Next, we have page ranking based on link and importance. Simply meaning how important a web page or person is in the network. Many important nodes pointing to you is then you have a high rank. Formula of page rank of V is equal to basic value plus a weighted sum of page ranks of node pointing to V. Let's understand the centrality measurement code. So first we just import our iGraph as IG. Next we create a empty graph g equals to ig.graph. Next we add 5 vertices. In between 5 vertices we just add the edges. 0 in between 0 and 1 we have a edge, 1 with 1 and 2 we have a edge, 2 and 3 we have edge, 1 and 4 we have a edge. So we name our vertices as A, B, C, D and E. We have our functions to calculate the degree centrality, closeness centrality, betweenness centrality and eigenvector centrality and page rank. So these are the predefined functions that we can use in iGraph, and this is the beauty of iGraph for that we so that we use it in a critical situation bestly. So we just print our centrality measures as a heading of our table. So we have a table of node, degree, closeness, betweenness, eigenvector, and page rank. For each vertices, we will print its name, its degree, its closeness, betweenness, eigenvector, and page rank. And for in this section, we just define G and we save G graph in centrality graph PNG where we label the node as a name or name like in previously we see that names of nodes are A, B, C, D, E and E. Vertex size as 40 and edge width are 2. Let's see image whether it is generated or not. This is not vertex graph. So this graph this doesn't generate. Oh, it didn't run till now. So if we run our code, see, you can see the output. So we have centrality measures as heading and the table, and using the predefined functions we get this value which are important to analyze the given graph. So if we see the graph explorer.exe dot, we can get the centrality graph. Yeah, looking at it, we can't verify closeness between a eigenvector and page rank, but we can verify our degree. So let's verify our degree section. So A has a direct connections between A and B. So the degree of A is 1. B has a direct connections with A, E and C. So B has degree 3. Now C has a double connection with B and D, double direct connection. So C has a degree 2. D has a one connection with C only, so we have degree 1. E has a direct connection with B only, so we have degree 1. So if we say the degree section is correct, we can think of that like the all the values rest are true as well. So these are the things that iGraph helps us very much in the section of large. Uh, these are the some important features of iGraph library that we need to know before doing analysis of graph. Using this library, we can do many network research like social media analysis used to find friend circle, influencers, fake accounts on Facebook, Instagram, and Twitter. Internet and computer networks used to analyze data flow, routing, and failures in computer networks. Transportation and maps used to find shortest routes in road, railway, and flight networks. Biological and medical research used to study gene networks, protein interaction, and disease spread. Business and marketing used to identify important customers and improve product recommendation. Crime and security analysis used to detect criminal groups and suspicious connections. Education and research used by students and scientists to study network behavior. Power grid and infrastructure used to check if electricity or water networks will fail when a node breaks. So these are the important research areas that we can do with our iGraph. Thank you.